I'll be the first to admit it. I got a little carried away on quartz and I recorded the longest lecture that I've ever recorded. Well, today I'll do my best to not repeat that incident with the continuation of tectosilicates, talking about the feldspar group. So I have this as F in this part of the notes, and we are into feldspars. Now, boy, feldspars are super important. They comprise a huge amount of the crust, both in the sedimentary, igneous, and metamorphic rocks. And to get into it, I want to discuss the structure of the feldspar group. And they tend to have a structure that's called a crankshaft. And what I want to do is I want to draw a crankshaft with you to start, and then we're going to use this drawing to explain how the formulas are all created for the feldspars. And to do this, what we have to do is draw like partial hexagons. So if we draw a partial hexagon, 1, 2, right? They have to have 6 faces, but we're not going to draw all 6. We're just going to draw 4. Okay, perfect. And then we put our tetrahedrons off of that. Okay, and then draw another little triangle coming off here, kind of like the sorosilicates. We're sharing that 1, and then use this base to make another hexagon. And then put tetrahedrons. And that, dear students, is a crankshaft structure that could continue on in this direction or in this direction. And then what ends up being interesting for this structure is that, okay, so at the tips, right, these are all of our bridging oxygens. Well, what ends up happening is that the centers of most of these are silica, right? Silica, 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 but not all. Sometimes there are aluminum 3 pluses that are the cation in the centers of some of these structures. And this aluminum is 3 plus, whereas the silicons are, 4 plus. And so we create a charge balance problem by substituting in some aluminums. And to accommodate that charge balance problem, big cations fit in the center parts of this part of the crankshaft. And so these are cations that are inserted for charge balance. Things like potassium, sodium, rubidium, calcium. Those are really important. So we need to put some notes now to work through this drawing. And what I want you to say is that aluminum 3 plus substitutes for some silicon 4 plus, causing a charge imbalance. Right? There's too many negatives now to go around. And so what needs to happen is it requires, causing a charge imbalance, requiring the addition of cations. And so these cations get substituted in because we've substituted these others, right? So what ends up happening, this is an interesting term. The term for this process is called coupled substitution. And the reason why it is coupled is that 2 things are happening. We are adding aluminum 3 plus, and as we add aluminum 3 plus to make charge balance, we must add, therefore, something like a sodium 1 plus or a potassium 1 plus. Now, if you were to add 2 aluminum 3 pluses, that it creates a negative 2 charge. And so what can happen is you get a coupled substitution of 1 calcium 2 plus. And this is the reason for the chemical formulas that you're going to see in the feldspars. What else in this early part of the notes? Oh yeah, let's put this as a crankshaft structure, just to give it a name, because a name will help you remember it. Now, at higher temperatures, so I guess we want to know is, where does that aluminum 3 plus go? Well, at high temperatures, it's randomly distributed. And then at lower temperatures, that aluminum gets partitioned in a more, I guess you could say, ordered way or less random way. So we have this as one part of our notes here. And then our second part of our notes is, where is the aluminum? I'm asking it as a question. Well, it depends on temperature. That's the answer. Depends on temperature. At high temperature, minerals that are high temperature minerals are random in their distribution of aluminum throughout the different tetrahedron. But at low temperatures, things become much more ordered. And this high temperature and low temperature random versus ordered structure is one of the reasons for the different names of our feldspars. Now, as we go through the feldspars, I want you to think of it all in terms of a triangle like this. This is a discrimination triangle that allows us to put names to explain the solid solution throughout the feldspars. And so we're going to put a little heading here with a little arrow, and it's going to say names for names using ternary discrimination diagram. Why? Because much solid solution. And we're going to first start by talking about the potassium M member. The potassium M member is also known as our potassium feldspars. And then, at the top of this triangle, and then we're going to talk about the plagioclase feldspars, which occur along a solid solution between the sodium M member and the calcium M member. But to start, let's go, and if you need to, you should pause this video and draw this triangle into your notes. It's definitely also in the textbook, but this is important for understanding feldspar organization. So to start, we're going to go into the potassium feldspars. That's an R, that's not a potassium feldspars. Now, these are oftentimes just called K-spars, because writing out potassium feldspar is very long, so we shorten it to K-spar, and you can do that if you want to here. The chemical formula for the K-spar is potassium aluminum Si3O8, where one aluminum has substituted in for one of the silicons, and it's required a coupled substitution and putting in this K. Should we make a note of that? Let's do it. Coupled KAl substitution. And there are three different polymorphs of the potassium feldspars that are controlled by temperature. So we're going to say three polymorphs controlled by temperature / ordering. The names of those three polymorphs are sanidine, orthoclase, and microcline. And only two of them need to really be memorized. It's going to be microcline and sanidine, because orthoclase is really hard to identify, and without a microscope, it basically just looks like microcline. So we're going to worry about sanidine, and we're going to worry about microcline. Before I show you a picture, no, I must show you a picture first. So let's put in a picture of these three. We'll write down some identification criteria and also some structural criteria. But sanidine is this one here. It ends up being phenocrysts inside of high temperature igneous rocks. Orthoclase here and microcline here. I purposely put white ones in because they might all be white. They could be clear, they could be pink. Well, microcline can be pink. Sanidine's only ever clear or white. But anyways, we'll put those things down in your notes in just a second. What I want to do, let's see, here we'll put it. We're going to put in a graph, because I said that the polymorphs are controlled by temperature and ordering. So what I want to have is temperature kind of on the y-axis. So we're going to call this cooling rate, where cooling rate can be very fast from magmatic temperatures down to cold earth temperatures, or it can be very slow. And on the x-axis, we're going to put order of the crystal lattice, where things are very well ordered, high order, and here is low order. And we can plot all three of these polymorphs onto this graph. And the things that are very rapidly cooled from high temperature but do have very low order is sanidine. Orthoclase sits in the middle. And the highest order but slowest cooled polymorph is microcline. And this is going to control the rock types that sanidine, microcline, and orthoclase are found in. So microcline is found in really slowly cooled rocks like granites and certain metamorphic rocks like gneisses, whereas sanidine is only in volcanics, where it goes from hot to cold really fast because the volcano erupts, blows the sanidine to their surface where it is quickly quenched. So only in volcanics for rapid quenching. All right, so before we move on to plagioclase, we need to get some of these notes formalized. Let's have the picture shown here as we go through the systematic mineralogy little bits to help you identify these different minerals. Sanidine forms tabular crystals in volcanic rocks. Only volcanic rocks. Don't ever say anything besides volcanic rocks. Specifically, rhyolites are the most common type of it. It may have, so it forms these tabular crystals. We see a beautiful example of a tabular crystal right there. Sometimes it has a twin plane through the middle of it, where one side shines back to your eye slightly different than the other, and this is called a Carlsbad twin. I would look for a Carlsbad twin if I'm trying to identify sanidine. There, it is light colored. It can be transparent. It is glassy, lustered, and then also it has two perfect cleavages. And those perfect cleavages end up being really important for its identification because something that's light colored and glassy could also be quartz in a volcanic rock. But if we see this beautiful cleavage flash, like in this picture here, we're like, oh, that's a perfect cleavage. This is a sanidine crystal. So maybe you could write a note to yourself that says quartz does not have a cleavage flash for helping you identify. Now, the other end member of our spectrum is microcline. And microcline has a lot of similar characteristics of sanidine. It tends to be tabular crystals, or cleaved masses. And I guess this heads to, what about the cleavage? Well, yeah, there are two perfect cleavages in this as well. So we would expect to find really nice cleavage flashes as we are handling microcline specimens. So that means we need to look for other things to help identify it. And it can be white or gray or pink or green. And the green variety is a special variety called Amazonite. Amazonite. But many times we're going to see microcline as the pink material that comprises granite. I'll throw in a picture of pink microcline. So we have the pink component of granite, or just as a big cleavage mass right here. Now, one thing that should catch your eye in this specimen and in this specimen is that there's a stripiness to it, almost like tiger stripes that go across microcline. In all microcline, you see this texture. And we need to put it in the notes and explain it briefly, and it is called perthite. Perthite texture. And we could draw perthite texture. Let's draw it over here. So let's say we have a cleaved mass, and on the cleavage face, we might see these somewhat irregular stripes going through the crystal. And what perthite is, it's an exsolution. Have we talked about that word this year much? Maybe not. Exsolution means unmixing. It's an unmixing of a solid solution that forms during very slow cooling. And let's try to put this down as a formal definition. It is it's a texture that forms by unmixing of solid solution during slow cooling. The stripes are a slightly different composition of feldspar than the main material. So the main material, oh boy, how do we explain this quickly? Well, the main material is just going to be pure KALSI308. But these stripes end up being pure NaSi3. AlSi3O8, which is also known as albite, plagioclase. Now, at high temperatures, before the unmixing occurred, maybe there was 5% albite mixed in with this potassium feldspar because there's a solid solution potential. But as cooling occurs, those two things can't stay mixed together anymore, and they must unmix. And as they unmix, they go through exsolution, which forms these stripes known as perthite texture. Is that enough? That'll have to be enough. You can learn more about it in later classes, like petrology perhaps next semester. This perthite can be seen in a variety of different ways. You can see it in gem materials. You can also see it under the microscope. So here's something you'll look for under the microscope, which is the tiger striping. See that irregularity? So this is under the microscope. You can see exsolution very microscope. And then in gemstones, this is a variety of gemstone called moonstone, which is a plagioclase that has this occurring at the microscopic level. And because it's occurring at the microscopic level, it diffracts light, kind of like how opal does, and you get this beautiful shimmering iridescence, pearly iridescence on the surface of plagioclase. Those are just an aside, common things to look for. Now, where do we see microcline? Well, I guess we hadn't quite finished defining microcline yet. Well, it's in any slowly cooled rock. We're going to look for slowly cooled, igneous, and metamorphic rocks. It's a very important rock forming mineral. All right, I hope that didn't get too messy for you, and instead you were just floored by fascination with potassium feldspar. And next we should talk about plagioclase feldspar. Plagioclase feldspar is a mouthful, also writing, and so many times you will hear a geologist just refer to it as plage. The story with plagioclase is that there's a complete solid solution between two end members. There's a complete solid solution here between sodium and calcium end members. And we have names for these two different end members. There is the NaAlSi3O8. This is called albite. And you could also give it a symbol of albite 100 is one end member. And there's a solid solution with mixing of sodium to calcium ratio that goes all the way up to the pure end member of calcium, aluminum 2 Si2O8. This is an end member called anorthite, and we could also give it the symbol of An100. And you could have compositions of plagioclase anywhere here along the way, and they all have different names, and you could also symbolize them different ways. So if it's close to An100 but not all the way, this might be AB30, An70. It has to sum to 100, but that would be a way to give a symbology to a plagioclase that has some composition intermediate along the solid solution. Now, I've already inserted this triangle once before. Maybe you've drawn it when you did before, but you can see the bottom of the identification or discrimination triangle has our albite 100 and AlSi3O8. We've got our anorthite, right, just like I said here. And then there's these other names, bitonite, labradorite, andesine, oligoclase. For the purposes of this class, I'm not going to have you learn these different names, okay? Just know anorthite and albite. Later classes, right? Later classes. Well, so I want you to say, learn the two end members. This is just a note to yourself. Learn the two end members. And I want you to know that that solid solution explains a lot of other geologic properties as well. So what we're going to do is we're going to draw some graphs, and we're going to plot the solid solution that we see in chemistry on graphs. So here is our AB100, here's our An100, that's our pure end member anorthite. Let's do another graph as well. We could do this for a lot of different important geologic parameters. Albite occurs in some geologic rocks, anorthite in others, and the solid solution of bitonite, labradorite, oligoclase, andesine, intermediate between them all. So here, let's do it again. Albite 100, anorthite 100. Well, what are we going to plot? Well, let's plot temperature. Where here is high temperature, and here is low temperature. Well, anorthite is the high temperature variety of plagioclase, and as systems go to lower and lower temperatures, compositions verge towards albite. So like in a magma, albite's forming in magmas that are 800 degrees Celsius, where anorthite is occurring in magmas that are like closer to 1100 degrees Celsius. Now what about silica content, SiO2 content? Well, albite is the high silica content, and anorthite is the low. So something like a rock with 75% weight SiO2 is going to crystallize albite, whereas something maybe with closer to 50% weight SiO2 is going to crystallize anorthite. And so just by identifying the type of plagioclase that you have, you can gain a lot of different geologic information as well. How do we identify plagioclase? Well, there's a couple keys to look for. And the number one thing to look for is polysynthetic twinning on cleavage planes. So what we're going to do is we're going to say, all right, so we're going to say tips for identification. Number one tip, of course, you can't help but look for color, and plagioclase tends to be light colored to gray. Light colored tends to be albite, whereas the darker grays tend to be anorthite. So you can sort of use color to identify. We're also going to look for cleavage. They all have two perfect cleavages. And it's on those cleavage fragments that we're going to look for this feature here that looks almost like mechanical grooves going all parallel to one another across the cleavage face. You can see it in the sample as well. This is called polysynthetic twinning. So we're going to put in polysynthetic twinning. And this is the dead giveaway that the sample you have is not orthoclase, it is not microcline, but it is plagioclase. Okay, this is really an important one. I'm going to put a star next to it. And what polysynthetic twinning is, it's these, we're going to say regular, almost mechanical looking fine stripes on cleavage faces. Okay. The reason for those stripes is this polysynthetic twinning. It occurs in one direction throughout the crystal. We should draw it in your notes since I'm just showing you pictures. Let's draw a tabular crystal, which is one of the ways that plagioclase can grow. Also, plagioclase can definitely have Carlsbad twin. So I'm putting in here a Carlsbad twin. Now in this example and in this example in the picture, there is no Carlsbad twin. I just added it for complexity. And then what we can see going, in this case, we're going to put in these stripes that go across the crystal very, very systematically. And we'll call that our polysynthetic twinning. Even at the microscopic level, this polysynthetic twinning can readily be seen, and it's the dead giveaway for identifying plagioclase as well under the microscope. So we can see those just repeated different amounts of brightness of light to gray to white, and that is polysynthetic twinning at the microscopic level. So that's how I want you to identify plagioclase, looking for the twinning. I've said that enough, right? The twinning matters. Okay, maybe that's because students forget that and have a hard time identifying plagioclase. Where do we see plagioclase? Well, it is in all rocks. Well, it's not in all rocks, but I guess I'm trying to say here is that it is a rock-forming mineral in igneous, metamorphic, and sedimentary systems. So important in rhyolites to gabbros to basalts. In metamorphic rocks, rhyolites, schists, they've all got them. In sedimentary, it's the detritus forming by erosion of the primary sources, and it can stick around enough in the sedimentary sequence to be a major component in things like sandstone. Well, that's it for the tectosilicates. There's other interesting minerals, but we don't have time for them. Plagin quartz is what you need to know. See you later.